Alright, welcome to the first lesson of Unit 4. Clearly, I'm not the only one that's really excited. Anyways, I want to quickly recap sort of where we've come from so we can understand how this unit fits into our overarching path. We started off with the necessity for coming up with what we call the limit of a function, and we spent the first unit taking limits of functions, understanding what that meant. In Unit 2, we use the limit to define the instantaneous rate of change for any function, which we named the derivative, which itself is actually a function, which told us the slope at any point along our curve. In Unit 3, we then came up with and derived a bunch of rules for taking the derivatives of many different types of functions, including a lot of very complex functions. And now what we're going to do is use the derivative to analyze a situation in much greater detail. And you'll be kind of surprised at just how powerful the derivative is. We can find out an incredible amount about a situation using the derivative in a lot of interesting ways. And so we're beginning with a fairly simple concept, and it will, of course, gain power as we move through. So we're going to start off with, given a function, defining and locating areas of increase and decrease algebraically by using the derivative. So to get us started, we have this situation here with this function f of x. And so what I want you to do is go ahead and sketch out this function and answer the 4 questions, and then use your answers to these 4 questions to fill in the blanks to the red sentences below. Alright, so here we have this function, and pretty clearly, there's some parts where the function is increasing, there's some parts where the part where the function is decreasing, and we want to just be able to clearly explain where those are. So the 2 intervals for which f is increasing, if we're just starting, we can kind of go through from the left to the right, and we notice as we are approaching the x value of a, the function is increasing. And so we can say that one interval where the function is increasing is for all values x less than a. Now if we continue on, notice here it's not increasing, but then past b it is increasing. Right? We notice that the function begins increasing, so another interval would be all values x greater than b. Alright, another way of writing that, I'll just write this above here. If I want to say that x is going to be less than a, I can say that on the interval from negative infinity to a, and of course I need to use curl brackets here because I'm not including either of those values. And another way to say that I'm going for all x values x greater than b is to write the open interval, again not including b, from b to positive infinity. Now we want to say what is true of the derivative of f on these intervals. Remember, the derivative of f represents the slope of the function at any point. So to help illustrate this, I'm actually going to draw the tangent line for a point on each of these intervals so we can clearly visualize what the derivative is going to be, because remember, the derivative of the function is the slope of the tangent. So you can clearly see here the tangent to the curve at any point on that interval, both those intervals that we defined, those tangent lines are going to have a positive slope. And so that means the derivative is going to be positive on these intervals. And of course, another way of writing that something is positive is to say that it is greater than 0. So you can say that f prime is greater than 0 on both these intervals. Alright, now moving on to the interval for which f is decreasing, and we can pretty clearly see that that is happening between a and b. And I'll go ahead and draw the tangent to the curve just to visualize that. And we can clearly see that the tangent to the curve for any point between a and b is going to be sloping downward, meaning the derivative at any point between a and b is going to be negative, or in other words, f prime will be less than 0. So we can write down the interval. This is when x is less than b, but greater than a. And of course, another way of writing that is on the interval from a to b. Notice I'm using curled brackets because I'm not including the point at a or the point at b. And f prime is less than 0 on this interval. F prime less than 0. So completing this, if blank, then a function f is increasing. And so we can kind of see here that if the function is going to be increasing, well, then we need the derivative to be greater than 0. All right? So if f prime is positive here, I'll just write POS. If f prime is positive, then a function is increasing, and similarly, if the derivative f prime is negative, then the function f is decreasing. And now there's one more thing that I want you to think about. You've already discovered the theorem that we're going to introduce, but I want you to think about what's actually happening right at A and right at B. And just kind of consider that for a second. It's a very important fact that is going to be key to us actually finding where a function is increasing and where it's decreasing. What you hopefully noticed is that right at A and right at B, the tangent to the curve would be perfectly horizontal. In other words, it would have a slope of 0. And that kind of makes sense, right? When something is going from increasing and then it changes to decreasing, there has to be some point where it's actually going to hit, be not increasing nor decreasing, be right at 0. And the same if it's going from decreasing to increasing. And so that's an important fact that we're going to make use of. All right, let's go ahead and actually capture this theorem now. All right, so this theorem is known as the increasing/decreasing test. A lot of theorems are known as tests because a theorem is always true, and having a certain test that always works is very valuable. So first, if the derivative f prime is greater than 0 on an interval, then the function f is increasing on that interval. If f prime is less than 0 on an interval, in other words it is negative, then f is decreasing on that interval. Now there's one important thing that is not technically a part of this test, but is really important, and that is that between increasing and decreasing, in between those intervals, there's got to be a point where f prime is equal to 0, or f prime is undefined. And kind of don't worry about f prime being undefined for right now. Really focus in on that there has to be a place where the tangent line is flat in between where it's sloped upward and where it's sloped downward. And these are known as critical points, either where the derivative is equal to 0 or where it's undefined. And that's the definition of a critical point. We've seen that before when we looked at rational functions. And this is going to be very, very helpful. So let's actually go ahead and take a look at an example that will allow us to see the progression through which I can decide whether something is increasing or decreasing. Alright, so we want to find the intervals on which this cubic function decreases. The first thing I want you to do is think what that means. What is it that I'm looking for if I'm trying to find where the function decreases? Well, based on this test here, a function will be decreasing if f prime is less than 0. So what we're looking for is where is f prime of x less than 0. And that's the first thing that you want to do when you're trying to find where something is increasing or decreasing. You want to rewrite the question in terms of what it is that you're going to be looking for. So we're going to be looking for where is f prime less than 0, because that means it will be decreasing. So clearly we now need to find the derivative, and that's actually pretty easy. So the derivative of f, we can just use the sum/difference rule and then take use the power rule for each term. So 4x cubed, derivative of that will be 12x squared. The derivative of 45x squared will be 90x to the first. And the derivative of 48x will be 48x And the derivative of a constant is 0, so the derivative of 60 will be 0. So here I have my derivative, and what I need to do now is set my derivative less than 0. So usually we're used to setting something equal to something, something else equal to 0, for example. But here we really want to be clear that we're looking for where the derivative is less than 0, so we're actually going to set it less than 0. All right, now we need to talk strategy for how we determine whether something is, where it's less than 0, where it's greater than 0. And what we were going to want to do is we're going to want to make a sign chart. And we're going to want to be able to clearly pick apart the places where it could be greater than or less than 0. And so the best way to do this is to actually determine exactly where it is 0, and then to look at each interval and determine whether it's going to be positive or negative. So in order to create our sign chart, what we're going to need to do is find the places where the function is actually equal to 0. And the best way to do that is to try and break your function up into factors. Breaking it up into factors will allow you to look at each factor independently and determine what will make that particular factor 0. Because when you're setting something equal to 0 and it's just a multiplication of different factors, you know that what will make the function 0 is what will make each individual factor equal to 0. So for many, many types of functions, this is very useful. In particular, a quadratic function. It's very, very useful. Now, you could, of course, use the quadratic formula. That would work just fine for finding what will make this equal to 0. But when you can, factoring is going to be the most helpful. So let's go ahead and factor here. Notice that you can take out a factor from 12, 90, and 48. That's going to be 6. That'll make it a little easier. So it'll be 6 times 2x squared minus 15x minus 8. And we can then factor this quadratic, and so you are going to have two factors here, two linear factors. And when we're factoring a quadratic, we're thinking, okay, what can we multiply together to get 2x squared? So you're going to need a 2x and an x. And then what can multiply together to be negative 8? Well, you got 1 and 8, or 2 and 4. Now you also have to remember you're going to need 2x times this plus x times this to equal negative 15x. And so if you think about that, well, if you use 8 and 1, 2 times 8 would be 16. 1 times x would be 1, obviously. So you'd have 16. You'd have 16 minus 1x, and that would work nicely, but you need this 15 to be negative. So you're going to want a negative 16 and a positive 1, which means that you will want negative 8 and positive 1. And if you multiply that all out, you'll get back our original polynomial. Now, of course, remember, you could still use the quadratic formula for a quadratic here. That's definitely an option. So keep in mind you can use that as well. Now I'm in a situation where I can clearly see the values that will make each of these factors equal to 0, and so this will allow me to create a sign chart here. I want to label what my sign chart is tracking the sign of. This is my derivative, so I'll label it f prime of x. And what I want to label on my sign chart are all the critical points. In this situation, we want to label where the function is equal to 0 so that we can clearly delineate and figure out where it's going to be less than 0. So we start with the first term that we can actually make 0, and that's 2x plus 1. You can set it equal to 0 and solve using inverse operations, or you can kind of just look at it and say, okay, this is going to have to turn into negative 1, so I'll have to take a half of 2, and it will have to be a negative in order for that to work. So negative 1/2, negative 1/2, and I like to label that with a 0 just so I can remember that that's where it's equal to 0. Later we will see some situations where the function is undefined, and that's also a critical point. So we will want to distinguish between where it's a 0 and where it's undefined. Looking at the second linear factor here, this will be 0 when x is equal to 8. And that again is a spot where it's equal to 0. So now I just need to determine for each interval, is it going to be positive or negative? So I start with something to the left of -1/2. An easy to choose, utilize number would be -1. You plug in -1, you get -2 plus 1, which is a negative. -1 minus 8, which is a negative. Negative times a negative is a positive. And so it will be positive. In between -1/2 and 8, and whenever I can use 0, I would like to use 0. It's the easiest. So 0 plus 1 is 0. 0 minus 8 is -8. That will make it a negative. Then picking a number in this interval over here, perhaps 10. 2 times 10 plus 1 is positive. 10 minus 8 is positive. And so I have positive. So now I can use my sign chart to go back and answer my original question, which is where is f prime of x less than 0? I've gone through, I've set it equal or less than 0, and I've factored so I can find the critical points, figure out where it could be less than 0, and that is on the interval less than 8, greater than -1/2. So I can write the interval in two ways. I could say where x is less than 8, but greater than -1/2, or equivalently, I could write on the interval between -1/2 and +8. Remember, I'm using the curled brackets here because at these exact points, the derivative is 0, meaning it has a horizontal tangent. And so these are equivalent ways of writing my answer. So there are a couple of key points here to take with you when you go through doing this, and I'll kind of just sort of label the steps here, if you will. First thing you want to do is rephrase your question. What is it that you're looking for? If something is you're looking for it's decreasing, you're looking for the derivatives less than 0, increasing where it's greater than 0. Then you obviously want to find your derivative and set equal, or less than or greater than 0. And then very importantly, you need to factor. That's going to be a crucial step. Factoring is going to be very important, and that will lead you to be able to create your sign chart, which ultimately will give you your interval, which you'll want to write correctly. All right, I'm going to go ahead and give you some to practice with. So long as you're following this framework, you're going to be able to determine where a function is increasing or decreasing using the increasing-decreasing test. All right, here are 3 problems for you to try. Make sure you're following as closely as possible the steps that we discussed for executing that test, the increasing-decreasing test. In particular, I can't stress this enough, how useful factoring the function will be in determining the critical points or zeros for your sign chart. And to check your answer, a great way to do that is to actually just graph the function and see if you were correct, if on your interval the function is increasing or decreasing or whatever it is that you're looking for. But only do that after you've attempted to solve this algebraically, because on the AP test, these questions will be on a non-calculator section, obviously. All right, be ready to present these then on Monday.